Thanks very much for having me here. I'm very happy today to talk about this joint work with Yao on the identification and estimation of dynamic structural models. But more importantly, this paper is actually about the unobserved choices, which I will immediately explain what it means. Okay. Any of your comments or feedback will be greatly appreciated. So to motivate the paper, let's think about in a review preference framework. We typically assume that the choices made by the agents are their optimal decisions and hence reflecting some of their underlying preferences. So because of that, the choices are usually considered as one of the key ingredients for our economic analysis, right? Well, the agent's decisions, unfortunately, in reality, may not be always directly or perfectly observed by researchers, and there are multiple reasons why this is the case, right? So first of all, if we think about the moral hazard problem, and what I mean by moral hazard here is essentially there exists information asymmetry between an agent and a principal. So an agent has his own incentives to maximize some objective functions, but they choose their best action, but these actions could potentially impose externalities on the other party, which is the principal, but the principal, unfortunately, may not be able to fully monitor what is going on from an agent's perspective, right? To give you a couple of concrete examples, in one of my other papers, I was studying the online credit markets where borrowers and lenders are interacting repeatedly over time. So in that context, borrowers are the agents. Once they receive the monetary transfer from lenders, they basically have incentives to maybe invest in riskier projects, or they may do whatever they like with the money in order to maximize their own payoffs. But these behaviors cannot be easily monitored by lenders, and it is even going to be more difficult for us as econometricians to know what is exactly going on from a borrower's perspective. So another example is related to the political economy, where you can imagine that there is a politician, for example, it's a governor. He or she knows exactly the amount of time or effort he spent in order to promoting economic growth, but this information is very unlikely to be observed by voters, or it's also pretty unlikely to be observed by us as researchers, right? So another reason why sometimes it may be very difficult to obtain the agent's choices could be related to the data collecting issues. For example, in economics, a lot of empirical questions are answered using survey data sets, but in many of the surveys, some of the key decisions of the individual, say their investment decisions on their human capital, on child development, or say their healthcare, stuff like that, may not be reported by the agent because of the concern of the privacy, or in some other cases, these questions may not even be asked in the survey because of the design of the survey. So there are multiple reasons why actually, in reality, it may be actually difficult for the researchers to observe the agent's choices. Given that situation, the main research question of this paper is basically trying to understand when the actions are hidden from researchers' perspective, what we can do in order to still uncover this decision-making process and to infer some of the preference parameters of the agents in order to, from the data, in order to do further analysis such as counterfactuals, right? In order to do that, we have to think about what kind of modeling assumptions we need to impose and what kind of data variations we will be using in order to recover the preference of the agents, even if their choices are not observed. Okay, so that's the main question of this paper. We can take a quick look at existing literature on the dynamic discrete choice models. So first of all, there is a long list of this kind of empirical work, but for most of the majority of them, the research papers are focused on the cases in which choices are observables. You can think of the RAS-type engine replacement decisions, individuals' retirement decision, occupational choices. All of these kind of informations are known to the researchers when they do this work. Okay. From a more theoretical perspective, if we think about the identification of dynamic discrete choice models, all of the papers that are listed here study the theoretical results for the identification of structural parameters, but all of these actually require the observation of agents' choices and some state variable for a set of random agents and for a period of time, right? And if we think about estimation, in the literature, there are two main strands of the literature. The first one is called the so-called the nested fixed point algorithm, which is proposed by Rust. And the other one is initiated by Hassan Miller in 1993, which is kind of a two-step estimation strategy. Well, in either of these two types of estimation strategies, agents' choices are needed. You need the choice to either construct a likelihood to do the estimation, or in a CCP type of the two-step method, you have to use the choice to do some non-parametric estimation of the choice probabilities or the state transition probabilities in the first step using the raw data, and then you can take that as given to your second step in order to estimate some more deep structural parameters, right? So basically, to summarize, the existing approaches are not generally effective when these choice variables are not observed by econometricians. And so for our paper, the main target is basically to solve this problem by providing more structures. Okay. So specifically what we do in this paper is to provide new identification and estimation methods for dynamic discrete choice models when the agent's actions are not observed. In our baseline analysis, we consider a very simple standard single agent finite horizon dynamic discrete choice model and with a continuous state variable. And we specify the state transition process through a non-parametric regression model plus some added variable, which I will be more specific when I talk about the model. We consider a couple of extensions to our baseline results. For example, we can allow that there exists some serially correlated unobserved heterogeneity, which is also not observed by econometricians. We can also allow for an infinite horizon model, but we definitely need more information for that case. We also consider a more practical scenario where maybe we don't have a continuous state variable. So what if there are only discrete state variables available? Then what can we do about it? Okay. So the last but not the least of our extension, we want to show that actually our identification intuition is not limited only to single agent dynamic discrete choice models. So we show that a similar kind of idea could be applied to deal with the dynamic discrete games of incomplete information, even if the choices are not observed in that case. Okay, so I will be mostly talking about the last extension because of time constraints. Okay. Following our identification strategy, we propose a sieve maximum likelihood estimator in order to estimate the non-parametric functions in the state transition process and also the agent's utility parameters. We also conduct Monte Carlo simulations in order to examine the finite sample performances of our proposed estimator. So this part is a little bit more like technical and related to more econometrics rather than intuition of identification. So I don't think I have time to go through the details, but in general, our estimator actually works pretty well. So that's kind of the punchline. Okay, but if I have time, I can show you some results. We also try to apply our method to an actual empirical setting. We basically try to study the moral hazard problems in the US gubernatorial elections. Specifically, we get a data set from another paper, which is collecting information on governors in the United States from 1950 to the 2000. And we basically estimate a dynamic discrete choice model for governors' effort exerting decision. So basically, in our model, the governor is the agent. He has a decision to think about whether or not I'm going to exert effort or I'm just going to shirk, right? These decisions is of course not observed by us, but these decisions will have an impact on the status of the economy, for example, which will have some measure for that. And we estimate the model, try to think about what are the utility preferences of the governors and how that affect their choices. Okay. And the quick results, basically we find that indeed, as the governors are approaching the end of their terms, they basically, there is a significant higher chance that they will exert less effort. And we also find some heterogeneity, which I will explain after I show you the model. Okay. This empirical application, it's related to some work in the political economy. A lot of paper I cited here basically try to study the impact of the institutional design of election rules. For example, they want to understand what is the impact of term limits on politicians' performances. And our paper here basically trying to also study this question by using a more structural method. But we will see the results later. Okay. So this is outline for the rest of the talk. As I said, I will first start with a very simple single-agent dynamic discrete choice model and give you some basic idea about how it works. Okay. So in the baseline results, we are thinking about a single-agent dynamic discrete choice model, but with a finite horizon. And we use t to be the index for each time period, and cap t is the last period. A couple of notations. So in the paper, we use st to be the observed state. So the state variable is observed from a econometric point of view. But we also have this epsilon t to represent the unobserved state, which is only observed by the agent, but is not observed by us econometricians. And the examples of this epsilon t could be just some utility shocks. Okay. So throughout the paper, we're going to use yt to represent agent's choices, which is an endogenous object, basically. The agent will solve his own optimization problem to decide whether or not to exert effort, for example. Okay. In each period, we can write down the agent's flow utility, which essentially depends on the realization of the state variables, both observed and unobserved, and also the choice he made. And given the structure, we can write down the sum of the discount utility stream of the agent like this, which is pretty straightforward. And here we use beta to denote the discount factor of the agent. Yes?
YT is a binary or it could be multiple?
It could be multiple, but I will mostly focus on the binary case just for illustration. Okay. So beta is a discount factor, and throughout the paper, we're going to assume that we know beta. And this is also the typical results in the current literature that it's, unless you have additional restriction, it's hard to identify the discount factor. Okay. So given the model, we can, the agent's problem is basically to choose some decision rule in order to maximize the expectation of the discounted sum of the discounted values. Here, the expectation is, of course, taken with respect to the transition process of the state variable and also the choices. But this transition process is also induced by the decision rule. So the optimal decision is basically choose a vector of delta for each period in a finite horizon game. Okay, so at this point, we're going to impose the following assumption in order to restrict our attention to a certain type of the model. First of all, we're going to assume that the dynamic process of the state variable and choice variable satisfy the first order Markov process. So this is typically adopted in the literature, but it could be generalized in order to allow for higher order Markov process. Okay, and we also, following the literature, the Ross paper, which is a seminal paper in the literature, to impose the following conditional independence assumption on the state transition process. And there are two implications for this conditional independence assumption. First of all, conditional on your current state, the realization of your utility shocks will be independent over time. Okay, and more than that, the transition for your observed state variable depends on your state variable in the last period, but also depending on choice, but is independent of your utility shocks in the previous period. Okay, that helps to reduce a lot of dimensionality issue, and which is typically also induced, adopted in the empirical literature. But of course, this conditional independence assumption is restrictive, and there are some more recent work trying to relax that by allowing these epsilons to be serially correlated. And in our main identification results, because we want to highlight the identification with respect to the unobserved choices rather than these complicated structure of the epsilons. So we want to stick with this more restrictive conditional independence assumption for our baseline results. But later we can show that actually we can take our model to a more complicated situation where the serial correlated heterogeneity is incorporated. Okay. The last part of our assumption one basically states that the state transition rules are time invariant. So no matter you are at your early periods or the ending periods, this one is always going to be the same. And this assumption is also typically imposed. And if you do observe agents' choices in the data set, you can basically test that. But in our case, because we don't observe the choices, so this is an assumption we have to make. And people have using the assumption a lot also in the literature. Okay. Given our model, we can write down, represent the agent's optimization problem using this Bellman's equation in a recursive way. And specifically because we assume that the utility shocks in the last period will not affect the realization of the future states. That's why in this last term, the conditional expectation of the value function does not its epsilons does not enter into here. Okay. Given the value function, the agent's decision is basically to simply choose a y, which is the choice, in order to maximize the value. And from the decision rule, if we integrate over the distribution of the epsilons conditional state, we can basically derive the probability that an alternative y is chosen conditional on the state. And this is the so-called conditional choice probabilities, which is also typically in the literature called the CCPs. And these are important equilibrium objects. Okay. And notice that in our CCPs, we have this subscript t in there because this is a finite horizon model. And in a finite horizon model, when you make your decisions, it's potentially non-stationary. You will make different decisions at the early periods versus the ending periods because the incentives are different. Okay. Okay, so this is the basic setup of the model. So in this slide, I'm basically trying to show you kind of a graphical illustration about the dynamic process of the state variable and the choice variable that is consistent with our assumption. So here, because the whole point of this talk is about unobserved choices, so in order to highlight that, I just add an asterisk to the y in order to indicate that this is unobserved from the econometrician's point of view. Okay, so basically what we see in this structure is essentially two things. The first part is highlighted in this yellow triangle, which is saying that my current state depends on my state in the last period. It also depends on my choices in the last period. And this whole thing in this triangle basically tells us some information about the state transition rules. Okay. And the second part, which is highlighted in this blue circle, it is basically talks about conditional on my current state, then I'm going to make some choices. And in the data, you will be able to see the conditional choice probability directly if you do see the choices. Okay. So to make it simple, basically, if this y, the choices, are observed from the econometrician's point of view, then we can estimate these two parts directly from the data, non-parametric or parametric, whatever you like. And this is exactly the key point in the Hudson-Miller type of a method. So you estimate these equilibrium objects from the data in the first step, and you take them to your second step as if they're known, and you can match the, you can solve the optimization problem to match with this equilibrium objects in order to back out more deeper structural utility parameters. Well, in our case, because we don't observe the agent's choices, so neither of them can be estimated from the data. So which means the original typical solution to this type of a model will not work. And this is the main challenging for our case if the choices are not observed. Okay. However, even if these two cannot be directly observed from the data, it doesn't mean that these two are completely irrelevant, right? So these two objects are still inherently connected with each other, with each other through this observed state transition process. So we don't observe the choices, but we do observe some state variables S, right? And to put it in the formula, so basically on the left-hand side of this equation, this is the density of a state S prime is realized, conditional on that the previous state is S. And this one can be written as a mixture of the true latent transition probabilities, while the choice probability, the probability that each alternative is chosen can be basically think of as like a mixture weights, right? So essentially, we do not observe these terms separately, but we do observe these state transition process from the data. And then the identification problem for this paper is basically reduced to how to use the observed state transition process in the data to recover these unknown parts from the model. And if we know the transition process and the choice probabilities, then we can just follow the Hudson-Miller type of the estimation strategy to do whatever we need. But the first step is basically how to identify these two from the, yeah.
So this restriction only has bite when that F, that inside F is like non-degenerate, like in the bus replacement.
Yes, right.
I know the age of the engine.
Yes.
So I always know when the choices.
Yes. So in the Ross type of model, this one actually doesn't really have a important meaning, because so even if I don't observe your choice, I know the mileage becomes 0 if you replace the engine, right? So it doesn't really. So in our case, we're more thinking about suppose there's an agent like a governor. He or she is choosing an effort. That effort will have some stochastic impact on the state variable, but we cannot fully recover their choices. Yes, but you're definitely right.
Differently, in that case, you can back up P either 0 or 1.
Yes, exactly. You directly, you can tell the choices, so you don't need to, exactly, yes. Okay. Okay, so this is the identification problem we're going to solve. Now let me talk about more detail, a little bit more details. Okay. But before that, let me still trying to give you some intuition in order to see what's the main variations in the data we're going to be using in order to identify other parameters. So for illustration, let's think about there are a sequence of time periods from period 1 to cap t. And there are two periods along the dynamic process, which is period tau and tau arrives earlier than t. Okay. So let's assume that at these two periods, the realization of the state variables are exactly the same, which is s. Okay. Then if we now at period tau, suppose we move one period forward, then we can write down the conditional distribution of the future state conditional as tau equals to s. Okay. And this is just as I explained in the last slides, is basically just a mixture of the true latent state transition probabilities and the choice probabilities are just some mixture weights. And you can do exactly the same thing for period t. Okay. Yeah. It depends on t because it's a finite horizon model. Yes. So that's why here it's I didn't have a subscript, but this is y tau and this is y t. Okay. So from our previous assumption 1, we have imposed assumption that the state transition rules are time invariant, which means no matter you're at period t or period tau, these two terms are going to be exactly the same. However, in the finite horizon model, the probability that an alternative is chosen is going to be different, which means these red part and the blue part, they are going to be different. And because of that, they generate differences in terms of the observed state variables, right? So put it in another way, for identification, if we see the differences in the observed state transition process at two periods of time, then we know that these differences are not coming from the state transition probabilities per se, but it's actually coming from the differences in the choice probabilities, which will be governed by some deep utility parameters, right? So that's kind of the key intuition for identification. And if you put it another way, you can think of in a finite horizon model, time is very important. So time is sort of like an exclusion restriction because time only affects your choice probabilities, but it does not affect your state transition probabilities. So that kind of exclusion restriction going to play a very important role. But if you think about this as an infinite horizon model, then the time will not be an exclusion restriction because the choice probability will be stationary over time. And for that case, we actually need some additional exclusion restrictions that may only affect the choices probabilities, but not affect the state transition probability. So that's kind of one of our extensions. But exclusion restriction is important. And finite horizon, time naturally serves as an exclusion restriction. Okay. In our model, we basically assume some structure on the state transition process. So we assume that this st plus 1 equals to the summation of two parts. And the first part, it's a non-parametric regression model, which is function m. And it's an unknown function, and it could be very flexible, but it depends on your choices in the last period and also your state variable in the last period. And we don't know the shape of m in the model. We don't have to know that. Okay. And it also adds up this eta, which represents some random shocks that affects the state transition process. And we assume that these random shocks are independent of the unobserved choice condition on the state variable, and for a normalization purposes, we assume that the conditional mean of the eta, which is the random shock, equals to 0. Okay. From the previous assumption 1, we know that the state transition process does not change over time, and given that structure, this is basically also implies that eta has a stationary distribution. The distribution of eta cannot also change over time by construction. Okay. So for illustration, now let's consider the identification for some fixed state S. And again, for illustration, I'm assuming that the agent can only take binary choice, either 1 or 0. Okay. And under this very specific case, basically, to identify the unknown functions M, basically is reduced to identifying two numbers, which is M1 and M0, and they are the values for the M function, given that the choices are 1 versus 0, and when the state is fixed at S. Okay. We can also define the choice probabilities at these two periods t and tau. We use pt and p tau to denote the probability that 1 is chosen. Okay, so that's just some notations. We also construct some conditional moments of the observed state variables. For example, we use mu t to be the first order conditional moments of a state variable, nu and psi to be the second and third order. So all of these conditional moments of the state variables are purely based on the observed state. So they can be directly estimated using the data. For identification purposes, we can just treat them as if we already know them, and they're just some constants we can get from the data. Okay. Great. Okay, now to think about identification. So remember mu t, it's the first order conditional mean of the state variable, which could be written as the following equation, where we are basically replacing future st plus 1 by our structure, which is the m function plus an epsilon plus an eta term. Okay. And remember that by assumption 2, we know this eta is independent of the unobserved choices. So which means we can basically get this eta term out of the summation, right? And we also make the normalization assumption that the conditional expectation of eta is 0, which means that part will just go away in the first order conditional moment. And essentially, we can rewrite our first order conditional mean of the state variable as a weighted average of M1 and M0. And the weights are just the probability that 1 is chosen versus 0 is chosen. Okay. And you can do exactly the same thing for period t and period tau. And this is the two equations after you do that. And from these two equations, the key observation is that if you know M1 and M0, then you can solve for P. You can solve for the choice probabilities. As long as this M1 is not equal to M0, because if they're equal, then there's no way to distinguish which is higher state versus lower state. Okay. So then our identification problem is basically to think about how to recover this M1 and M0, which is the key parameters in the state transition process. If we do know that, then we can easily back out our choice probabilities. Okay. So this is the first order conditional moments. Then if we think about the higher order conditional moments of the state variable, this procedure is very similar, but now the only thing is that in the equation, we get this term, which is highlighted in red. This is basically the higher order conditional moments of the error term, which is eta, right? And unlike the first order case, we can basically know that the conditional mean is 0 by normalization. But now, in these higher order moments, we actually don't know what's the value of these conditional expectation of eta, right? And that's basically introduce more unknowns to our system if we want to pin down what is the value of M1 and M0. And if you keep using higher order moments, again, you will still never know the unknowns for conditional moments of eta. Okay. But now, recall that we have argued that the conditional distribution of eta is stationary, which means that no matter you're at period t and period tau, these conditional moments of the error terms will remain the same. So from this observation, it's easy to think that now we can just use the variations across different time periods in order to get rid of this eta. And this is exactly what we are going to do next. Okay. So basically what we do is to take a difference between these second order and third order moments of the observed state to get rid of the etas. And now this equation, even though it looks quite complicated, it's still only incorporated a couple of things. So on the left-hand side, that's the differences between some observables. And on the right-hand side, it involves these choice probabilities, which are in red, and it involves the M1 and M0, which some unknown parameter of interest. And it also involves these mu's, which are also the known constant from the data. Okay. But also remember that from these slides, we have derived the formula for the choice probabilities. As long as we know M1 and M0, we can back out P. Okay. So if we take that formula to these two equations, basically the P's are gone. So everything remains is just M1, M0, and some known constants from the data. So that basically gave us two equations, two nonlinear equations of M1 and M0, but there are only two unknowns, which are M1 and M0. And in the next slides, I'm basically going to show that given the system, we can actually get a closed form solution for M1 and M0, which is kind of very nice if you want to do the estimation like constructively. Okay. So if we call the summation and the product of M1 and M0 to be delta 1 and delta 2, then you can do like a very basic, maybe high school algebra to derive the formula for delta 1 and delta 2. It looks like ugly, but essentially it's on the right-hand side is everything. You can just use the observed conditional moments of the state variable, nothing new. And if you know delta 1 and delta 2, basically M1 and M0, they are just two solutions to this quadratic form equation, provided that they does have two solutions, and also the two solutions are not equal to each other. And these conditions here is also testable just using the data. Okay. So then you get two numbers from two solutions to this quadratic equation, and then the only remaining step you want to understand is that which is M0 and which is M1, right? Any questions? Okay. So there are many different, so basically in order to decide which one is M0, which one is M1, you have to impose some ordering conditions, right? From the data, you can't directly tell which one is which because they are associated with some unknown choices, so you don't know which one is which. So in our paper, we propose one example, which can be used to tell you the differences between M1 and M0, which is suppose y equals to 1 means that the agent exerts effort, and y equals to 0 means that they don't. Then we can assume that conditional on the agent works hard, the state distribution, the future state distribution, first order stochastically dominates the one where the agent does not work hard. So this is just one example that tells you that if this is the case, then M1 is larger than M0. But you can come up with any other ordering conditions according to your empirical application. So it doesn't really matter how you tell the difference between M1 and M0. And also, it doesn't really matter if you can always switch the order of these two and label them one of them each. Okay. So once we identify this M1 and M0, then we can basically recover the choice probability, use that very simple formula. Yeah.
So if I understand correctly, you need at least 4 periods?
3. So you can use it. So if they're overlapping, you need 3. Yes.
So which means when there are more than 3, you have over-identified conditions?
When you do your estimation, yes, you can use them all together and to estimate. Which yes, and you can potentially also test using these overriding restrictions. Yes. So now we have pinned down M1 and M0, and then we know PT and P tau. The other thing we don't know so far is the conditional distribution of the error term eta, because we know the conditional mean is 0, but we don't know really the shape of the eta. So in order to recover that, we can write down the state transition process of the observed variable, but using the conditional distribution of the eta. So here we're basically evaluate the conditional density of eta at S prime minus M1 and S prime minus M0, and this weights are still the choice probabilities. Okay, and again, the stationarity of the eta distribution plays a super important role because given that, we know that these conditional densities will be the same across different periods, but the choice probabilities are not, and we already know what are the choice probabilities. So from these two equations, you can solve for this red term and the blue term. And if you use different value of S prime, then you can basically trace out the conditional density function for eta at different values. Okay, yeah, question?
How does it scale with the cardinality of y? Smaller moments?
If you have more if your y increases, basically now you will get more unknowns, like M1, M0, M2, and then you will get a larger system of nonlinear equations. Right.
Then you need more periods.
Potentially, yes. Okay. Okay, now we have already also pinned down the distribution of eta, and this is basically just a summary of what I have just said. Given that I only have 5 minutes left, so I will just skip, as I expect, about this estimation and simulation results. But essentially, what we're doing is similar to maximum likelihood, but it's not exactly the same because our estimation have to deal with this non-parametric functions of M and also the distribution of eta, which is also non-parametric in our case. And we instead use the sieve maximum likelihood, which is basically you are kind of using some approximating like polynomials or some other basis functions to approximate the non-parametric functions. And I'm happy to talk about that part offline if you're interested. Okay, sorry, this is, I want to talk about the one of the extensions we get in this paper. Basically is about the dynamic discrete games of incomplete information. So in our setting, previously we were focusing on the single agent model, but consider now we have a game, and I index for each individual. So suppose these players choose an action from an action set simultaneously at each period, and we use this bold Y to be the action profile. And suppose each player at each period observe their state variable, which is also publicly observed by other players and also observed by econometricians. And epsilon t denote the utility shock, which is only privately observed by the agent, but not by any other players, not by us also. Okay. Unlike the single agent game, now the agent's utility depends on not only my information, but also depending on other people's choices and other people's state. And here, this S and Y, they're bold because that represents the profile of the actions and states.
It's infinite horizon?
It is infinite horizon because this T could be going to infinity, yes. But it also should apply for the finite horizon. But I'm just thinking infinite horizon is more general, or it doesn't have to be. Okay. So we consider a pure strategy Markov perfect equilibrium of the game, and we can define the player i's equilibrium choice probability conditional on a state profile as this P star. So if the agent's choices are actually observed by econometricians, then you can use the very similar two-step method, which has been discussed in the literature for a while. You can basically recover this equilibrium choice probability from the data directly and estimate the transitions of the state also from the data. And then you take that, which is an equilibrium object, into the second step to estimate other utility parameters. Well, in our case, we do not observe the agent's choices. So we have to make some additional assumptions in order to recover the parameters. Specifically, we're assuming that we impose additional structure on the state transition process. We're assuming that conditional on the current value of the player's action and the state, the future states are independent across players. So this assumption basically is motivated by some empirical setting in the dynamic oligopoly computation. So if you can think about that, the state variable is my capacity level. The choices is just my incremental choices to changes to capacity. Then what is my future capacity looks like doesn't really depend on other people's choices or the states. It only depends on my choice and my previous state. Okay, and if that is the case, you can think about for player I, this is the state transition process. is a mixture of the latent state transition process and also the mixture of the weights is the choice probabilities. By assumption, we assume that this part only depends on my own state, but in the game setup, the choice probability will naturally depend on everybody else's state. So in the game setting, basically, the S negative I, so other people's state variables will be serving as an exclusion restriction. So this is kind of like what I find kind of interesting and natural in the game setup. And if you have this kind of exclusion restriction, then you can do whatever similar in our baseline model to identify the choice probability and state transition process. So I don't, how many? I don't have any time.
1 or 2 minutes.
Okay, 2 minutes. Okay, let me just quickly talk about our empirical application, which I have already said a little bit. So we have this data for governors, and basically, after we clean the data, we essentially have 142 governors, and they are called the lame ducks from using some jargon in the political economy. So basically, what this means is that these governors are not eligible for re-election. And there are 2 possible cases for that. So in some cases, in some states, basically, all the governors are allowed to only be in the office for 4 years. In some other states, it could be multiple, could be at most 2 consecutive terms, and each term is 4 years. And for that cases, we only incorporate the governors who were serving their second term. The reason we do that is basically to get rid of this re-election incentives in the governor's optimization problem, just to make things simple. But definitely re-election incentives is important. Okay, so we have some observed characteristics of the governor. We also observe this log of per capita spending, which we use as the indicator for how well the economy is doing for the state. And I don't have time to show you the details, but what we're using is just basically taking our baseline model, saying that the state variable follows, the transition follows that structure, and we have a very simple linear utility function for the governor's choices. And we got estimates, and we also try to compute the probability that the governor is shirking for year 1, which is the time that he or she got re-elected, and 4 is the period that he will leave the office. And we do find that as the governors are approaching the end, they're basically more likely to shirk. And we also find that for people who were serving their second terms compared to their first terms are more cost effective, and which is kind of interesting because you can imagine that people who got re-elected may be inherently different from those who just got the first term because they already survived their first term and they got re-elected. And this is, we call the selection effect of the elections. And yeah, so this is everything I want to talk about. Thanks so much for being here. Thanks.
Questions? No more? Okay.
Yeah.
What would be a useful counterfactual in this context? It would be sort of extending the period.
You mean in this political in government? For example, you can. Yeah, it could be something like that, or you can think about change their incentive schemes, or change their after they leave the office, change their I don't know, change their. So for example, if they care more about the future after they leave the office, what they're gonna do, or something like that. Their career concerns, stuff like that.
But that's sort of exogenous to your model, no?
But
Capital T.
in our model, it's exogenous, but you have to understand the agent's utility preferences in order to do that counterfactuals, which is actually not typically done in the existing literature of this political economy, because they are mostly using more regression analysis and stuff like that.
Good. Thank you very much.